Okay, so let's continue. Last lecture we saw energy band diagrams. We were trying to see how to what all information can we gain from energy band diagram, and this was the diagram for an MOS system that we had, and so it was a metal here and a silicon dioxide here and a semiconductor here, and we said that lots of interesting information of course we can get from here. It's a p-type semiconductor. As we approached the interface here, we saw that the semiconductor was becoming intrinsic here and then was becoming an n-type here. And also from a diagram like this we could obtain the voltage, the built-in voltage between the metal and the semiconductor. One can see here that the vacuum level that you see here, E naught, goes down and comes here. So a difference in vacuum level here and here denote the presence of the voltage between these two places here. And we said the voltage difference between here and here, which we call as the psi ms, the voltage of the metal here minus the voltage in the semiconductor here, we can determine by doing something like a Kirchhoff's voltage law here, or conservation of energy. We start from this point here, we go here, we add the energy that is needed to promote, let's say, an electron from here to here. Then we promote it here, we add up the energy, then we come down here, so we subtract this much amount here, right? And then we come down back to here, and then we subtract this much amount. So we started from the same energy here, and we ended up at the same energy here. And so whatever energy increments you add and subtract, they must all add up to 0 here. And this is what we had done here. This particular part here is this, from here to here is energy gap minus the 0.02 is the gap here, plus 4.05 electron affinity of silicon here, minus IMS is this point here, and minus 4.2 is the work function of the metal here. And we do that and we equate it to 0, and we get the built-in voltage here, psi ms, which we found as 0.77 here. All right. Note that this is the internal voltage which comes about because the metal has a work function which is different from the work function of the semiconductor. And as we said, anytime you place two different materials with different work functions, you will end up with a contact potential between them here. All right. Also, I had mentioned that please keep in mind that this is a potential between this point here in metal and the semiconductor here. And this should not lead to a false impression that I have a system in equilibrium and how come I still have a voltage across it. We said that you have to keep in mind that this is the diagram that we have drawn. But in addition, this is more realistic, that you have a metal wire which connects the two together. And therefore, if you construct an energy diagram starting from here till here, this is what we had constructed. But along with that, remember, this part is also there. So as we construct this one, we'll see that the drop from here to here is exactly balanced by a drop from here to here. And the net drop turns out to be 0 as expected because we are shorting it with a wire. All right, so let's continue. Another energy diagram for you. Okay, so in this case also we have a metal with a work function of 4.2 eV. We have EC, we have the Fermi energy, EI, EV, all of them are here. And what can we conclude from here? What is the material type? Yeah. EI is the intrinsic level. Intrinsic level. So what is the material type? N-type, because it's closer. EF is over EI, and EF is closer to EC, so it's an N-type. And what is happening as I approach the metal? See, the distance between EC and EF is increasing, which means that the region is getting gradually depleted of electrons. Electron concentration is decreasing here, right? Electron concentration is decreasing. And of course, the system is in equilibrium. EF is flat throughout. And can we find out what is the difference, the voltage difference between metal and a semiconductor? You are seeing that E naught is going like this here, and E naught going like this, which means the voltage here and the voltage here are different, because voltage is minus E naught by Q plus constant here. So can we find out what is the voltage difference? What is the procedure? Start at EF, go up to EC. Do we know this value here? Difference between EF and EC. If I know the electron concentration, I know how much is EC minus EF, right? So I can go from here and come up to this point. And then from EC, I can come up to E0. Do I know that? EC to E0? This is the electron affinity. Then from here to here, I'll go up, right? Which is the potential difference. And then you come down, 4.2, right? And you're back to EF. And therefore, as you do that, you will be able to get this potential difference between these 2 points here. Okay. Another thing that you note here is that if I want my electrons to go from semiconductor to the metal, if I want my electrons, suppose I have a contact here and I would like to have a current flow with electrons flowing from semiconductor to metal, you can see here the electrons will see a barrier here. If an electron starts from here, it has to go over this particular barrier here, and then it can go into the metal here. So one can see an existence of a barrier potential here. Similarly, if I look at from the metal side, if I start from the metal side, electrons are all here, but then from the here it has to go to the conduction band here. Again, we see a barrier here. And can we estimate how much is the barrier here? How much will be the barrier? See, how much is the difference between EC and E0 here? Electron affinity, which is 4.05. And how much is this? 4.2. Right? So you know the barrier between these 2 points here. So you can determine, so by sketching these energy diagrams, you can find out how much is the potential difference between metal and the semiconductor. You can find out what is the value of this barrier here. Okay, so lots of interesting information you can obtain from here. All right, here is another energy diagram. What is this telling us? What all can we get from here? Equilibrium, fine. What else? This material is N-type. This material, P-type, all right. Now, vacuum level is continuous, right? Vacuum level is continuous. So that's fine here. What is happening here? What is happening here? Note that, conduction band here. So if I look at the conduction band, the difference between conduction band and E0 gives me what? Electron affinity. So electron affinity of this side, if I look at the material a little bit left to it, there's a certain electron affinity. If I look at the material to the right of it, I have a larger electron affinity, right? What does it imply? Two different materials. Two different semiconductors, because for a semiconductor, electron affinity is same. Irrespective of what doping you do, what voltage you apply, electron affinity is a constant. So I see here that when I go from here to here, when I see a discontinuity here, it indicates a discontinuity in electron affinity. So it indicates that I have two different materials. I have two different materials here. Okay, so that's where these problems or these discontinuities are coming, and similarly a discontinuity there is coming. Okay, so we know it's N-type and we know it's P-type. So it is a p-n junction, but it's a p-n junction made out of two different material here. And one can see here, this is a larger gap material and this is a smaller gap material here. So what we call this as a heterojunction. Why? Because it's two different material. Okay, so one can see that. And similarly, if I give you the values, as an example, this is aluminum gallium arsenide, a material here, and this is gallium arsenide here. Okay, this has a band gap of 1.42, this is 1.8. Electron affinity note is 3.82 here. The electron affinity of gallium arsenide is 4.07. So now, given this information, these values are known, of course. Band gap and electron affinities are known, and band gap and electron affinity is known. So now, given this, I can obtain lots of interesting information. I can find out what is the discontinuity here, right? Because discontinuity will be equal to what? 4.07 minus 3.82, right? So right there, 4.07 minus 3.82 will give you how much is the discontinuity here. Similarly, you can find out how much is the discontinuity here. All right. If I ask you what is the total voltage, so this is a p-n junction, p side here and n side here. What is the net built-in voltage here, QVBI? How do we do that? We'll do the same thing here. You start from here. Do I know the difference here between this and this? That will depend on doping. So it will depend on doping. So you start from here, go up here, then go up to this particular point. We know this here. Then go up to this particular point here, QVBI. Come down here. We know this here. Come down to this particular point here. We know this what this point is because we know EF minus EV. So as you do that, as you go around the loop, starting from here, and as you go around the loop and come back here, you will end up getting the value of QVVI. What is the built-in voltage inside my heterojunction here? Okay. All right. What is this? Lots of energy diagrams. What is this energy diagram of? Huh? N, P, and N, right? So NPN transistor. That's what the energy band diagram is here, right? So anyway, so we'll look into these things in more detail. Now, the reason why I'm emphasizing so much on energy band diagram, you go back into, again, history of semiconductors, and you go, there is a very nice lecture by Bardeen, one of the inventors of the transistor, a Nobel lecture here, and you read his Nobel lecture. These are one of the earliest instances of somebody using energy band diagram. So you look at the Nobel lecture, and you find, and Nobel lectures are, pitched to general audience, right? And so Bardeen had to explain the working of the transistor, how semiconductor works. And you can see that how liberally the energy band diagrams are being used to convey what semiconductors are, how transistors behave, or how p-n junction, So you can see here it's a semi band here, EC, the conduction band here and the valence band here and EG here. So a diagram like that showing electrons here and holes here. The hatched region shows that it's primarily full, completely full, except for few vacant spaces here. You can see EF closer to EC, so N-type semiconductor, EF closer to EV, P-type semiconductor. I'll just skip over. We just saw this, right? A metal semiconductor, how the energy band diagram goes. This is for an early MOS system. Metal. So there's a metal here, metal plate, and then there is some insulator, air insulator or something else, and then there's a semiconductor, right? And so the energy gaps trying to explain how this MOS device works using energy band diagrams again. Okay. All right. Here is another person, another Nobel laureate, Herbert Kroemer. And I just wanted to put, he has this, just to convey to you the importance of energy band diagrams. So he has this, he says the importance of energy band diagrams. He likes to put it in the form of Kroemer's lemma of proven ignorance. And what he says is, if in discussing a semiconductor problem, you cannot draw an energy band diagram, this shows that you don't know what you're talking about. Okay? If you can't draw, this means you don't know what you're talking about. If you can draw one, but don't, then your audience won't know what you're talking about. All right. So it's emphasizing the importance of energy band diagrams, right? So all these stalwarts in the field of semiconductors, they all say that energy band diagrams help you gain insight into the operation of the device. All right. So what we have been doing so far is looking at, I've given you energy diagrams, and I said, what can you, when you read it, what information can you get? All right. But of course, we are also interested in sketching energy diagrams. How do I sketch it here? Okay. So how do I start? So let's do that with a number of examples here. So the first thing is, suppose I have first of all, if I have a simple N-type semiconductor uniformly doped, there's no problem. Energy band diagram is EC, EV, EF, right? So that's very simple. So the next simple case is, suppose I have N-type silicon only, but one side has uniform doping, let's say 10 to the power 16, and other side has uniform doping 10 to the power 18. How do I sketch the energy band diagram of such a system here? All right. So the steps are, now just follow these steps, and the same steps we do for all semiconductor devices. We just repeat them. So what we do is, if I want, note that the two semiconductors are in contact, so they are in thermal equilibrium. Okay. So first what I do is, I imagine them to be isolated. So separate them out. You want to energy band diagram of this system. This has two distinct parts. Separate those two distinct parts here. So now they are isolated. Okay, they're no longer in thermal equilibrium. Why did we separate them out? Because we know that each individual part is very simple. Its energy diagram we can simply write. right? I can just go ahead and write what is the energy band diagram of this silicon. I can also write what is the energy band diagram of this silicon. So individual components energy band diagram I can very simply write here. Then what I will do is I'll try and bring them close together and then see what happens. Okay, so that's the strategy. So first you write down energy band diagram of each individual part which is separate, and then you combine them here. Okay, so let's see. So these are the two parts separate. How do I write energy band diagram of two separate parts, two isolated parts of semiconductor? The first starting point, keep in mind, is E naught. There is no charge here. There is no charge here. The vacuum level that you see here is constant, E0. So you start off by drawing a constant E0. All right. So that's the first step. The next step is the moment I know E0, I know where the conduction band of this particular material will lie. It is silicon, so conduction band will lie. Electron affinity below that. How much is it? 4.05 for silicon. So I can immediately write EC here for this part. The moment you know EC, of course, you know EV. EV is just band gap below EV. So I can write this down. And if you know the doping here or the number of electrons here, you can write down where the EF is of this part here. So this is an isolated piece of N-type semiconductor. So I can draw its energy band diagram. Now similarly go for this side. All right, so I know, remember this equation, N0 is NC exponent minus EC minus EF by KT. So if I know N0, I know EC minus EF. So similarly, write down this part here. So this is also silicon for us. So again, I measure 4.05 from here, draw EC, draw EV here, below band gap. Then I know the 10 to the power 18, so I know where is EF here. EF will be much closer to the conduction band here, so I draw this. So I have energy band diagram of my isolated system. Now comes the interesting part. Now start imagining that these two semiconductors are brought into contact with each other. The moment they are brought into contact with each other, see, there are two ways in which you can bring them into contact. One is you simply put them into contact. Another, and they will attain thermal equilibrium. The other way is also, remember that if I connect them by a wire between here and here, that will also allow them to exchange electrons and they will also come to equilibrium. Okay, so you can connect a wire between these two and they will also come to equilibrium. But let's imagine that we are bringing both of them together here. And in yesterday's lecture, I emphasized that if I bring them together, note that EF here is higher as compared to EF here. And if EF here is higher as compared to EF here, that's an indicator that if you bring them into contact, electrons are going to flow from this material to this particular material. The gradient in EF denotes the direction of current flow here. So electrons are going to flow from here, this material to this particular material. So now as electrons flow, what will happen? This particular material will become positively charged. This particular material will become negatively charged. What will be the direction of field? Like this here, right? Like field here. What will it do to my E0 here? E0 indicates the direction of field. So this E0 will start coming down. As it comes down, now note, as it comes down, because electron affinity is a constant, the whole diagram here that you see from here to here, it starts coming down, right? And it starts coming down. Eventually, as more and more electrons transfer, this EF will line up with this EF. And as it lines up, equilibrium has been attained, no more flow of current. So this is what is happening now. Electrons are flowing from higher Fermi energy to lower Fermi energy. And this is what is creating a field, a potential difference, and this part starts coming down. Okay, so let's sketch the energy band diagram in equilibrium here. So in equilibrium, the starting point is what? Constant EF. No longer constant E0. Because note that a field and a voltage is already developed. So E0 is no longer constant anymore. Right? So a constant EF is what you draw. So you draw EF throughout the system. The next thing what you draw is, you draw a line indicating what is the interface between these two materials here. Okay, draw a line here. The interface between them. This side was, remember, this side was all 10 to the power 17. This side was 10 to the power 18. Now, the other thing is, as electrons flow from here to here, note that what happens is changes occur, because note that this part will get depleted of electrons and this part, some accumulation of electrons will occur. All these things occur close to the interface here. Okay, close to the interface. As you go far away from the interface, your semiconductor is pretty much the same. And as you go far away, your semiconductor is pretty much the same. Okay, So what you do is you sketch the energy band diagram far away from the interface. Okay. So for example, once I know EF, I can sketch far away from the interface that my EC is going to be here and EV is going to be here, right? Far away. So my semiconductor far away from the interface will be untouched by what has happened at the interface. Okay. All right. So we say EC and EF here. Similarly, far away from the interface, my semiconductor is going to look like this, because note, conduction band is closer to the Fermi energy. So I can locate where my EC is. Once I know EF, I know EF minus EC minus EF here, so I can locate EC, I can locate EF. So you've done that. Far away. All right. Once you know EC, what you can do is, do you know EV here, E0 here at this point? Just go electron affinity above. And you know E0 also here. And you know E0 also here. Now, what is going to happen? E0 has to be continuous. I made a statement and showed it to you that E0 has to be continuous. So as you approach, what will happen is this E0 will go up and join this here. We don't know the exact variation. Energy band diagrams don't give you quantitative information on how it goes. For that, you'll have to solve Poisson's equation. Okay, but we can connect this up. Okay, we can connect through a smooth curve here like this. All right. Now, once it goes like this here, how will this go? This is always below vacuum level by electron affinity. So it will also go like this here. And it will also go like this here. And our energy band diagram is complete. We have a complete energy band diagram at equilibrium. Okay, once you have that, now you go ahead, you know these values here and you know these values here. You can find out how much is the potential difference and all that. You can determine. Okay. All right. So, so we'll repeat this. All right. And we can find out using this psi equal to minus E naught by Q. We said start from this particular point, go up here, come to this particular point and go down here. And you will find out how much is the potential difference, built-in potential difference between these 2 points. Okay. Let's do that for a PN junction. All right. So what is the starting point now? What should I do? Huh? Isolate the two. This is, I know, p-type and n-type, so break it apart. So first you break it and then you make it. All right. So that's what you have to do here. So p-type and n-type. Okay. Then what do I do? Draw the energy band diagram of the isolated system. What is the starting point? E naught. What do I do next? Locate EC. Locate EC. All right. Once I know EC, I know EV. Locate EF. How? From the doping. Locate it here, EF, right? Do the same thing here. Locate it here, EC here, this one here. This is n-type, so Fermi energy is going to be closer here. Do that here. So that's the energy band diagram of the isolated system. Now, I'm going to bring them into contact, and what will happen? Electrons are going to flow from higher to here. All right. The same thing, another way of saying is the holes are going to flow from here to here also. Okay. Although I'm not drawing it. So electrons are going to flow from here to here. So as they flow, what happens? Electrons are getting here. So this will become positively charged and this will become negatively charged. So what will happen to E0 here? It will start to go down. Remember, as things get positively charged, in terms of energy, it starts coming down. So E0 here will start coming down. Eventually, this EF will line up with this. Okay. So let's do that. Energy band diagram in equilibrium. What is the starting point? EF is constant throughout. So draw in EF constant throughout. Next step. No. Next step. No. Draw the interface. Draw the interface. Okay. This is where my interface is. Draw that. All right. Next. No, where EC? Far away from this interface, things are going to be the same. Your N-type, P-type is going to look like P-type. No problem. N-type is going to look like the standard N-type. So you locate now. Once you know EF, you know where the EC is going to be and where the EV is going to be. So do that here. Far away. Okay. Similarly, do that here. All right. So locate that. Then E naught. E naught will go above electron affinity here. I know E naught here. I know E naught here. Next thing. Connecting them up. It has to go up like this. So you connect it up by a smooth curve here. Right? Connect it up here. Same. It follows exactly the same here and follows exactly the same here. And there. You have the energy band diagram of your PN junction, right? Okay, so everybody's comfortable? How to draw? Okay, then draw for this. Okay, all of you take out a sheet and do this. Do this and please write your name and submit. This will be our sort of first mini quiz. Okay. If you want help, I'll help you. Okay. If you get stuck, ask so that I'll help you. So I've given you a tough one. I did the easy one, but this is a slightly tough one. But same steps. There's no difference. Yeah. EG is the gap between EC and EV. Yes. Energy gap between the two. See, that's what happens when you listen. You feel as if you're understanding, right? Until you do it, you start doing it yourself. Yeah. Yeah. The doping is same 10 to the power 17. So assume electron concentration is same. Which one? B. Right. It is B. It's for EGB and psi B. Electron affinity for B. See, what matters is not the absolute value of the energies. What matters is the relative values. Okay, so you just draw EF, one straight line, and then start locating the rest of the energy levels. EC minus EF, if you want, let's say it's N type, take about 0.2. 0.2 EV. Similarly, if you want for P type, EV minus EF, take 0.2. Okay. All right, let's look at the solution. Everybody done? Or you need some more time? A little bit more time? Okay. Okay, so let's look at the solution now. All right. So let's start again as usual. We separate them out, A and B. Separate them out. Draw a constant E0. Locate the energy band diagram of semiconductor A. So that's going to be 3.8 below. This is a N-type semiconductor. So, and this is 3.8. And this point here would be 5.6 here. 3.8 plus the energy gap. So it's 5.6 below the vacuum level here. Similarly, locate the semiconductor B. That's 4.07. And this is the conduction band. This is the valence band is 5.47, 4.07 plus 1.4. So that's at 5.47 EV. And EF is closer to valence band. And we said let's assume it to be 0.2 here and 0.2 here. So that's sort of easy to do. The next thing is we note that what will happen is EF is higher here and lower here. Electrons are going to flow from here to here. Electrons are going to flow from here to here. And what will happen is then this will get positively charged and so this will start moving down. Which means the vacuum level here will start moving down as compared to the vacuum level here. Okay. All right. So let's have equilibrium then. The starting point is EF, constant throughout. You draw that. Then the next point is draw the interface. Draw the interface here. Far away from the interface, things are the same as before. So we do this here. We locate where far away this semiconductor is. So EC is close to EF here and EV is here. So yes. Yeah. So it should be below that. Yeah, right. These are qualitative diagram. It's not been drawn to scale, right? Yeah, you're right. 5.6 should be below this here. True. So EC and EV are here. And similarly, we can go ahead and locate where EC and EV for, on this side of the junction are. So we locate it here. We know that it's closer to EF, so it is somewhere here. And its EC would be somewhere over here, right? So we locate these points here. What is the next step? We draw E0. So we draw E0 here. We draw it over here, keeping in mind this is 3.8. And similarly, we draw it here, keeping in mind this is 4.07. And we note that this was going to go up, right? It was going to go up. So now how is it going to go up? Well, it will go like this here. E0 will be continuous. All right. So we've drawn that. Okay, no problem. Now start with EC. EC will be, this is 4.07. That's what I think all of you are making the mistake, 4.07. So it starts to come down, right? But then the moment I come here, so I am going down 4.07, 4.07, and I come here. The moment I go towards the left of the interface, I have to come down 3.8. And therefore, that's the discontinuity. So I come down 3.8 here. So it comes down here at this point, 3.8 here. Now I start coming back here and then go on. Okay, so I had to, from here, I have to come down 3.8 and then I go here. Now, once you know EC, then of course you know EV, and then of course you know the whole thing here. And of course, you have to keep in mind how much it is coming down, so you will see how much is this discontinuity and how much is this discontinuity here. All right, so that's the energy diagram. What is the built-in voltage of this energy diagram, of this system? How do we do that? Now, we all know, start from EF, go up here, come down here, and then come back to EF. Right? That's what you have to do. You have to start from EF and come back to EF, go like this here and come back here. Assume that this voltage here, EF minus EV, is 0.2, and similarly EC minus EF is 0.2, and I'm sure you can get how much is the built-in voltage of this particular system. All right. Okay, one last example. Let's sketch this MOS capacitor. Okay, metal, silicon dioxide, and N-type semiconductor here. So let's. You want to do it? Huh? Okay, go ahead, do it. MOS, sketch it out. All right. So information that you need is the following. Let me put it. All right. Separate. I think all of you can sketch if I give you the value. What do you need for metal? What information do you need about the metal to sketch its energy diagram? Work function, right? SiO2, think of it like a wide band gap semiconductor. So what you need is again electron affinity and energy gap. And this is silicon, electron affinity, energy gap. So once you isolated each other, note that the energy band diagram is going to look like this here. E0, this is, let's say this 4.7 work function. Silicon, this is 4.05, we know that. This will be 5.17 silicon here. And SiO2, okay, so this is N-type, this is over here. And SiO2 is like this. Electron affinity is approximately 1. Energy gap of SiO2 is approximately 9. So this point is 10. So I've given you the isolated energy diagram, right? Now you build the diagram in equilibrium. Energy band diagram in equilibrium. So these are informations. If one has information on all of these, then one can sketch it up. Okay, so that's not a big issue. Now you put them into contact and see what happens here. And please, if you put them into contact, you will say that equilibrium will occur. You would want electron to go from higher from energy to lower. And if it's bothering you, how will it go through SiO2? Right? How will it go through SiO2? Remember that I can also short these two together by a wire and bring them in thermal equilibrium. So don't let that bother you. Think that the electrons are transferring. Okay? Because I've connected them up through a wire here. I've connected them up so electrons can transfer. Okay? And an insulator, no matter how much insulating it is, will allow a little bit of current to flow. Will allow charge to flow. Okay? There's nothing like infinite resistivity. So if you leave it for long enough time, the charge from here will leak through SiO2 and come to the metal. Okay, so even in that case, you will reach equilibrium. Okay, shall we look at the solution? All right, so let's see. First step, constant Fermi energy. Let's draw it. Now we have two interfaces, so let's draw two lines here. Okay, one interface here and the other interface here. Let's draw two lines. Again, far away from the interfaces, everything is fine. All right, so we can locate this here. EC will be very close to EF here, and EV again we can locate. All right, so we can do that. And the next thing is, let's locate the vacuum level. So let's look at the vacuum level here. Vacuum level is over here. And vacuum level is 4.7 and this is 4.05, so no problem. As I approach, note that vacuum level is going to go up, obviously. So let's put this here, goes up. Okay, we can put these all up, so no problem here. Now the moment I come here, vacuum level will go like this here. All right, will eventually, there cannot be a discontinuity in vacuum level, so vacuum level will go here and join up with this one. Now that I know this one here, I can locate 1 eV below the EC of SiO2 and EV of this one here, and your energy band diagram is complete. Energy band diagram of your metal oxide n-type semiconductor. The energy band diagram goes like this here, and you find that this E0 is higher than this E0, which means metal is positive as compared to the semiconductor here. So there is a built-in voltage. And how much is the built-in voltage? Again, you can find out if you start from here. EC minus EF is, let's say, 0.2. So 0.2 plus 4.05 plus the built-in voltage. So you come here minus 4.7 and you're back to the same point. And therefore, you know how much is the built-in voltage of this particular system, MOS here. Where was the difficulty? In how to handle SiO2. All right, so what we did was we went up till here, and then we said it has to be continuous. We are not bothering about, as I said, what is the exact variation. Okay, note that there would be a curvature here of this particular part because there are charges here. In the silicon dioxide, there is no charge, so it will go straight. It will, because the slope of E0 gives us electric field, and electric field has to be constant. So this will be linear here, while this may not be linear here. Okay, so it will go here and join up with this one. Okay, so let's stop here, and please submit the